So let the recording begin. Yeah. Okay. So last day, what we had seen was something like this. We had first of all talked about a bunch of bosons, bosonic atoms or molecules in 3D, and we had calculated that the density of states, G of epsilon, that is the number of states between epsilon and d epsilon, divided of course by d epsilon per unit energy interval, turned out to be something like this. And then we had used this Bose-Einstein distribution. Sorry. And using these two together, we had calculated the number of particles which the system would have at any given temperature T by simply integrating. Now, this, of course, is the number of states between energy epsilon and epsilon plus d epsilon by d epsilon, of course, per unit volume. So, this small m is the number of particles per unit volume, which is calculated by using this. And after some manipulations, what we ended up with was this result. Where Z is e to the beta mu and G alpha Z is a series of functions, of course, a different function for each value of alpha, which is given by this infinite sum. So in particular, what we have is sum with p running from 1 to infinity of z to the p by p to the 3 by 2. Now, I must make a correction for the term I use for this quantity. I'm not very sure, but I think I said something like this being the occupation probability, right? Did I use that word?
Yes, sir.
Well, that actually is wrong. And in fact, I told you why it's wrong, right? Because we saw that this number could very well exceed 1, right? Because e to the beta epsilon minus mu would be pretty close to 1, especially if epsilon is very close to mu. So this number could very well be more than 1, which of course means it cannot be a probability. But what it really is the occupancy or expected occupancy. That is, if you have a microscopic state with energy epsilon, on average, how many bosons would be there? That is what this Bose-Einstein distribution talks about. In fact, when you talk about the Fermi-Dirac distribution, which is essentially very similar, but you have a plus sign here, there the number is always less than 1. But there also what you're really talking about is what is the average number of fermions that would be there in a given state. That number, of course, has to be less than 1 because the number of fermions can be only 0 or 1. So their average can only be less than 1. And here, since you have the possibility of putting more than one boson in a given state, it's very possible that this number will exceed 1. So it's not really a probability, it's the occupancy or expected occupancy, to be more precise. Okay? And there, of course, we have this quantity mu, which is the chemical potential. And as I said, this formula is actually not that useful to calculate N at a given temperature. What this really tells you is you should be able to solve this to find out Z for a given N and T. Okay, so this really tells you what the chemical potential can be. But as we saw in the last class, the real problem lies in the fact that this G3 by 2 Z is bounded above. By the way, this series, as is defined, only converges for z less than 1, or less than equal to 1 rather. For z more than 1, this diverges. But we have already seen earlier that because this thing is a number of bosons in a given state, this can never be negative, which means mu has to be less than epsilon, and it has to be less than the least of the epsilons, which is 0. So mu has to be less than 0. So z, which is e to the beta mu, is just can only go right up to 1, but can never even reach 1, actually, strictly speaking. Okay. Now, before we go any further, let us just take a look at the properties of this function. Some basic look at the property of this function, because that's going to be useful. So this function is of course defined only between z going from 0 to 1. Beyond z equal to 1, this series diverges. Okay. So 0 to 1. Now what is G3 by 2 0? Can anybody tell me that? That should be obvious from this formula. Yes? What is the value of this function when z is 0? Maybe it will be easier to understand if we wrote this out as a series. This is actually z to the 1 by 1 to the 3 by 2. Right? So I'm talking of G3 by 2, of course, here, plus z squared by z cube by 3 to the 3 by 2, and so on. So how much is the value of G3 by 2 at z equal to 0?
So it is 0 now.
Yeah, it has to be 0. What is the derivative?
0, sir.
Are you sure?
1.
The derivative is 1.
The derivative is 1. Of course, when you differentiate this gives you 1. All the other terms have z in it, so they vanish. Okay. At the other end, G3 by 2, 1, that's actually zeta 3 by 2. That is a well-defined and well-known value. You can either look up a table or sum it up on a computer yourself to find out that this is about 2.612 and so on. And what about the derivative? If I were to differentiate G alpha z with respect to z, you will get p z to the p minus 1, right? Here, for every term. And that p will cancel this p. At least one part of this p, and this will give you p to the alpha minus 1 below. Okay? So we'll have the sum of z to the p minus 1 by p to the alpha minus 1. Now, for z equal to 1, which is where you're looking at this will simply be 1 over p to the alpha minus 1 summed over, in other words, zeta of alpha minus 1. In this case, zeta of half. Any idea of how much this is? Zeta of half? Just to remind you, zeta s, the Riemann zeta function is 1 by 1 to the s, plus 1 by 2 to the s, plus 1 by 3 to the s, and so on. This infinite series. So what's the value of this series as s equal to half? Any idea?
Minus 1.5.
Well, that would sound a bit strange, right? These are all positive numbers which you're adding up. Right? You're adding up a bunch of positive numbers. Would you expect the sum to be negative? Yes? Okay, for s equal to 1, this is zeta 1. Can you tell me what this is? Sum of 1, half, 1/3, 1/4, 1/5. This is called the harmonic sum. That is sum of all the reciprocals of integers. Any idea how much this is? Yes? Okay, just to digress a bit, if you were to plot these values for every n, that is for 1 you plot 1, for 2 you plot half, for 3 you plot 1/3, 1/4, and so on, then what you get when you join these points smoothly, one curve that of course joins these points smoothly is 1 by x, right? Now, the area that we are looking, this sum that we are looking at, that's basically this area. 1, half, 1/3, 1/4, 1/5, right? Is that okay? This is the height of 1, width of 1. This is from 0. This is the height of half, width of 1 again, height of 1/3, width of half again, and so on. So this sum that we have here is less, as you can see, than the area under this particular curve. So any idea how much this is?
So this is ln x
Yeah, but what happens when you integrate that from infinity to 0
0 to infinity.
or 0 to infinity? What do you get? What is ln infinity?
So it's
Yes,
infinity only. ln.
you're right. So this actually diverges. Okay, this is the so-called harmonic sum, which actually is infinitely big. In other words, if you give this is an infinite series and you sum up sufficiently large number of terms, can exceed any number that you want to. Okay, that's what this is really telling you. And it's telling you that zeta 1 diverges. So what can you say about zeta half? Zeta half is 1 by root 1 plus 1 by root 2 plus 1 by root 3 and so on. If you compare it with this series, the one which I know diverges, what can you say about each term here? This term is the same as this, right? What about this one? Compared to this term in zeta, this is zeta 1, which I know is infinite. I'm trying to compare this with zeta half. Now, if you look at the comparison, these two terms are equal. What about these two terms? Which one is bigger? The lower one or the upper one? Among these two terms, I mean half and 1 by root 2, which one is bigger?
So 1 by root 2 term is bigger.
What about this? Compared to 1/3, of course.
So it is also bigger than 1 third.
Yeah, so what you can see is every term in zeta half actually is larger than the corresponding term in zeta 1. So what do you conclude about zeta half?
Sir, this seed should also diverge.
Yeah, because this one has to be bigger than zeta 1, right? If it were finite, you would say that zeta half is definitely larger than zeta 1. But because zeta 1 diverges, the only possible conclusion is zeta half is also infinitely big, which means this is infinity. The derivative is infinity. And what does derivative of infinity mean? it means that the curve there is vertical, right?
Yes,
Derivative
sir.
of 0 curve is flat, infinity means the curve is vertical. So basically, when you try plotting this graph, it will look something like this. Sorry, you have to excuse my poor drawing skills, but this is what G3 by 2 Z will look like. Okay, the slope here, this angle should really be 45 degrees, and it is. Remember, the two sides are not being drawn to the same scale. This is one is this big on the Z axis. On the vertical axis, this much is 2.612. So in that scale, this is really a 45-degree angle or slope of 1. Okay. So that's what this curve should look like. Okay. It monotonically rises from z equal to 0 all the way to z equal to 1, but reaches a finite value there. Okay.
Answer.
So it's important to know this because you have to have some feel of what these functions actually mean. Saying that n equals this quantity with g3 by 2z really doesn't tell you much unless you know what g3 by 2z looks like. Okay? Sort of looks like this. It goes and vertically meets this point, which is where the curve ends, because for z bigger than 1, the series is simply not defined. And anyway, we are not even interested in that because we know that our mu can never exceed 0. So our z can never exceed 1. Okay, fine. So this was our result ultimately. N is a bunch of constants, m, k, b, t. Well, not really a constant. T is the temperature. The rest are constants. 2 pi, sorry, not pi square, pi h cross square to the power 3 by 2 times g3 by 2z. And as we have seen, this increases with rising z. And as we argued in the last class, this really is something which should give us the value of z given n and t. However, notice that z can only rise all the way up to 1 and cannot go beyond that. And so there's something crazy happening when z reaches 1, because what you see is you get an upper bound on n, the number of particles that the system can have. Okay, and the temperature at which z reaches 1 for a given n is called the critical temperature. This is important. Also called the bosonic condensation temperature, but we are going to come to that later. Tc. And so our Tc is defined by this formula, n equals mkb Tc by 2 pi h cross square into G3 by 2 1, which is zeta 3 by 2 or 2.612. That's the numerical value. In other words, Tc for a given n can be calculated using this formula. It's 2 pi h cross square by mkb into n by 2.612 to the power 2 by 3. Just inverting this equation. So for a given n, you can calculate the critical temperature. Now, the question really is the following. What happens when, okay? Now, why is that a question? Because apparently it looks like when T falls below Tc, this is the formula for n. When T falls below Tc, this factor should be more than 2.612 to be able to give you the number of particles which are there in your system. But this number, as we have already seen, can never exceed 2.612. And that means apparently you have more particles in your system. That is, your n is larger than it's allowed to be. The maximum possible value of n at a given temperature is given by this times the maximum value of G3 by 2z, that is 2.612. If n is more than that, then apparently your count is missing a few particles. Not a few particles, a large number of particles. The mystery is what happens to the extra bosons. Okay, are you with me so far? This is the most important question. In other words, if I start with a particular system, I can always, given the temperature, I can always find a Z for which this will match. Both sides will match, and you're happy. You have got your temperature. At that temperature, this is the value of the chemical potential, and that's what gives you the total number of particles. Now, if you keep on lowering the temperature, you will reach Tc, this particular temperature, this formula that we have here. And at that temperature, N will still be equal to the value given by this formula, but G3/2Z will take its largest possible value, which is 2.612. If now temperature falls below this value, then this factor will become smaller, but this cannot become any larger because it has already reached the maximum possible value of 2.612, which happens when Z reaches its maximum possible value of 1. In other words, this whole thing becomes smaller than the N. The number of particles you can have by your count apparently is less than the number of particles you have in your system. Is this problem clear? The solution we are going to come to, but the problem is clear, right?
Yes, sir.
Okay. Now, you all know the solution because you've already studied this topic once before. But just to sort of understand this better, let me just take a quick detour into what happens with photons. So we can do a similar calculation with photons as well, right? So what happens there? That's the question. And for that, what you have to remember is that certain things change for photons. One of the first things which changes is that the Bose-Einstein distribution changes a bit. It's not e to the beta epsilon minus mu minus 1, it's just this. No mu for photons. Remember, mu basically comes from the fact that total number of particles, if you impose the constraint that total number of particles is conserved, then this parameter mu comes into the picture. If you remember your derivation of the Bose-Einstein distribution, you actually had two Lagrange multipliers in the calculation. I'm assuming you have done this calculation where you found out the number of ways you could arrange the system in and then maximize that. You have done that, right?
Yes, sir.
That calculation. The derivation of this expression, I mean. There are several ways of deriving this expression, but one of the standard ones, or the epsilon minus mu one with the mu, there what you do is you assume, you start with a picture that different energy levels have different degeneracies. So you have G1, G2 as a number of, this G is not the same as G of epsilon in a way, although similar. This is the number of states for every energy. So one energy level with energy epsilon 1, there are actually G1 states, then for epsilon 2, there are G2 states, and so on. And then you say, okay, I'm going to put in N1 bosons here, N2 bosons here, and so on, and find out the number of ways in which you can do the distribution. So I think you have done this calculation. Have you?
Yes.
This looks familiar. Yes or no?
Yes.
Yes,
Yes,
sir. We
sir.
have done.
You've done this, right? Yeah. So what did you do when you solved, when you use this to find out the distribution? What you did was to maximize this W, or rather log of this W, because that's easier to handle. But you had these extra conditions. You had the conditions that if you add up this, you're going to get the total energy of the system, which is fixed. And if you were to add up this, you will get the total number of particles in the system, which is also fixed. But this is not for the for the photon. This is for general bosons which have conserved numbers. And then in the calculation, you put in two Lagrange multipliers in order to maximize this log W. You put in a multiplier beta here and a multiplier mu here, and then handle the problem. Okay? I hope you remember that. And that's where the beta and the mu came into the picture. And only later, when you identified this with thermodynamics, you could relate that beta is actually 1 by temperature and mu is the chemical potential, which is gives energy per molecule or per entity. Now, the point is the mu comes into the picture only because of this particular conservation law. The total number of particles is fixed. For photons, there is no such conservation law. Photons can be created or destroyed. So for photons, mu, you shouldn't really say mu is zero. You should say there is no mu. The concept of mu doesn't even arise for a photon. Okay. And of course, mathematically, this looks exactly the same as the Fermi, the Bose-Einstein distribution we have used so far, but we have put in mu equal to zero, right? So with the photon, the first change is the distribution changes to 1 by e to the beta epsilon minus 1. But there are other things which change. First of all, density of states, G epsilon, D epsilon. This calculation essentially goes the same way as before. You do get 4 pi k square dk, and you do get 1 by 2 pi cube, exactly the same way as you had before. One major change is there's an extra 2. Remember where this extra factor of 2 comes from? Yes?
Sir, it comes due to polarization of light.
Number of photons that have energies between epsilon and or number of states which have energies between epsilon and epsilon plus d epsilon. For a photon, you have an extra factor of 2. Where does this 2 come from?
Sir,
All this, remember, something which you have already done before.
does this come from the polarization of light?
Yes?
Polarization, due to polarization of light.
Even for electrons, you have an extra factor of 2. Compared to the count that we have done. The count that we have done and the thing we have been working with are for spinless bosons. So there you did not have this factor. For electrons, you have a 2. For photons, you have a 2. But where does that come from? Yes?
So for electrons,
For
it is
electrons, this 2 is actually the spin factor. There are 2 different spins, which actually, for the same k, you have 2 different spins. So that's why you have to multiply that by a factor of 2. For photons, for the same k, for the same wave number, you have 2 different what? Quickly, we don't have all day. You know this, right? Yes? These are the polarization states of the photon. That is, the state is not given only by the wave number. You also have to specify the polarization state. So the wave number is taken care of by the k, but you have to have 2 possible polarization states for the same k. That's where the 2 comes from. Or, in other words, this simply becomes k square dk by pi square. So there's an extra factor of 2, but that's not really a big difference. The really big difference is the energy to k relationship. What's the energy to k relationship for a photon? What we had was this, h cross square k square by twice. That's what we used. But that was for non-relativistic bosons that we were talking about. For photons, what would this formula be? How is the energy related to the wave number? Yes.
So H cut C K.
Okay, what's the formula that you know for the energy of a photon?
Sir, E equals to PC. So
Yes.
if we replace P equals
But
to
that's
H,
a formula which everybody knows, right? That's something which you have been almost born with. Or rather, okay, from high school you have known this formula for the energy of a photon. What is it? The silence, well, is making me nervous that I'm not even connected. I am, I hope.
Sir, H nu.
Come on. For energy of a photon, Einstein's formula. Actually, Planck's formula, which Einstein adapted to a photon. What is the energy given by? H times what?
Sir, H nu.
Now I'm getting really nervous. Am I still connected? Okay, just tell me. I'm connected, right?
Hai, sir.
sir,
Am I?
you can't hear our voice, sir. Hello, sir. Sir, please. Keyboard boy.
Okay, are you saying something which I can't hear for some reason?
Yes, sir.
Okay, sorry. I must have. That was the problem. Okay, the problem was at my end. Sorry, my earphone came loose.
Oh,
Okay, so all of you know this, right? H cross omega. So what's the connection with K? Omega is
sir, epsilon equals to H cut CK.
right. And when you use that with K square dk and replace it by epsilon, you end up with G epsilon, which is given by epsilon square d epsilon. Well, epsilon and K are proportional to each other, so K square dk becomes epsilon square d epsilon, but with a H cross cube C cube factor down below. So if we do the same calculation that we did for photons, the number of photons at a given temperature, and here there's no chemical potential to worry about, turns out to be something very similar. So let's quickly see what that's going to be. That's going to be epsilon squared d epsilon by pi square h cross square cube c cube. That's the g epsilon times e to the beta epsilon minus 1, which is the number of photons per state. And if you integrate this, again, the integral will essentially go exactly the same way. You can put the pi square h cross cube c cube outside, and you're going to get and when you calculate this integral, what you're going to get that's just this factor. And this integral is something which can easily evaluate, and it will come out to be theta 3. Very similar to the calculation that we have done before. And that's a constant fixed number. So we can directly show that n goes as t cube. Now, here too, here what happens is as temperature changes, the number of photons change. N varies as t cube. But why is that not a problem? Earlier, remember what our problem was? We had some n, and as temperature changed in this formula, for a system with a given number of n, as temperature changes, n cannot change, so this thing had to adjust. The chemical potential had to keep on adjusting until this formula was satisfied. But the problem was the chemical potential could only increase up to 1, and then G3 by 2 Z could not go beyond 2.612, and that's where the trouble came from. Here we don't even have a Z to adjust. We already have n given as a function of t. So why is that not a problem here? Here also as t changes, n changes, right? That couldn't happen here. For our photons, for our bosons with bosonic atoms, As temperature changed, N had to stay the same, so Z had to adjust. And the whole problem was Z could not adjust beyond a particular limit, which is where the puzzle comes from. Here, on the other hand, for photons, as temperature changes, N keeps on changing. So why is that not a problem? Why don't we have a mystery like where did the extra photons go? Yes? Suppose I lower the temperature, then T cube decreases, right? So N becomes less. So you had more photons, suddenly the number of photons have gone down. Why is that not a problem?
So here we do not have any constant like earlier. There is no zeta function, so it would not.
Okay, that zeta function is okay. You do have a zeta function. You have zeta of 3 in the integral. But I guess what you mean is you don't have a z to worry about. Or G3 by 2z or something like that. Right? But okay, physically what you are saying is close to being correct. Physically, what really is the issue is number of photons going down is not a problem because number of photons is not conserved. And why? Because photons can be created or destroyed. Okay? You can absorb photons, you can create new photons, and that's allowed because that's a relativistic process in which particles can be created out of energy. That cannot happen in the non-relativistic world. Our atoms will simply not go away. Okay. So while this similar thing, although the formula looks different, but the ultimate feature is similar. A similar thing happens for photons as well, but for photons it's not an issue. Number conservation was never a problem with photons. So here what happens is number of photons goes down with temperature, and that's not a problem at all. But this is something which simply cannot happen. So let's go back to our photons. Let's go back to our bosonic molecules or atoms. This bosonic gas that we are dealing with, there the number of particles is fixed. You simply cannot decrease that. Okay? So the question about what happens when T is less than Tc becomes very important. And to answer this, you also know where the answer really lies. You counted the number of states between K and K plus dk using this formula, right?
Yes, sir.
And when we did that, we are definitely making errors, right? Because we are saying that you are taking this thin shell between or thin shell between two spheres of radii root over twice m epsilon by h cross square and root over twice m epsilon plus d epsilon by h cross square and so on. And you are counting the number of states that are there simply by dividing this by the volume per state. But the volume per states that you have are on a rectangular lattice. And so there will always be some states which will stick outside, some states which will just go in. So this will give you some amount of error. That error would typically be tiny. And one state which this count definitely misses is that this is 0 for k equal to 0. So we have not counted the ground state. Now, usually this is not a big issue for the simple reason that in a given microscopic state, you will have typically a few particles at best. If they were fermions, you could have only 0 or 1 particles. And if this is not a fermion but a boson, you would typically have a small number, maybe even thousands. But compared to the number of bosons in the system, which is of the order of 10 to the 23 or more, depending, of course, on the amount of substance you're talking about, that would be a tiny, tiny number. So we would not really be bothered about missing out on a particular few particles. However, here we are saying that, okay, maybe my n at a particular so suppose we have a particular number of particles, some macroscopically large number of particles which make up our system. Now, if I make Tc go down by a factor of say 4, Tc to the 3 by 2 goes down by a factor of 8. So if temperature goes below Tc by a factor of 4, so if you look at T equals Tc by 4, N falls by a factor of 8. So it's not a small number of particles which are going missing. It's a macroscopically large number. 1/8 of the particles you can find, 7/8 are going missing. So you realize that what we are saying here is that we have a problem that we are missing a huge number of particles, not just a few. But if you look at this at mu equal to 0, which is the upper limit that we can possibly reach, the ground state occupation number, what is that? That's going to be e to the beta epsilon minus 1 with mu equals 0. And that, since epsilon is 0, this actually goes to infinity. So missing out on the ground state may have a huge issue, because if mu really reaches 0, then the ground state should be infinitely occupied. Now, we don't really have an infinite number of particles, which really means that although we have been saying what happens when mu reaches 0, z reaches 1, mu never really reaches 0. Okay. Notice that, the ground state occupancy, we're just looking at the ground state now, nothing else. N0 is given by 1 by e to the power minus beta mu minus 1, right? Epsilon is 0 for the ground state. So this is the number of particles in the ground state. And as mu gets closer and closer to 0, this number becomes closer and closer to 1. And therefore, this N0 becomes larger and larger. So for a given N0, given number of particles in the ground state, we have it's a minus beta mu is actually, we just take the reciprocal and add 1. And this means and if N0 is macroscopically large, that means it's of the order of 10 to the 23 or so, then of course this is a very tiny number. And for a very tiny number, x log of 1 plus x is approximately how much?
0, sir.
Oh, for x, yeah, that's true. But if you go look beyond that, as a series log of 1 plus x, what is that? Remember the series for log of 1 plus x is x minus x squared by 2 factorial and so, sorry, minus x squared by 2 plus x cubed by 3 and so on. So for very tiny x, log of 1 plus x is really like x. So this is approximately, at least, for a macroscopic occupation, this is like minus kBt by n0. So mu doesn't really reach 0, but mu actually reaches a value which is very close to 0. It's minus kBt, the thermal energy, divided by the number of particles in the ground state, which now, in our scenario where we are missing a lot of particles and the only place they can go is in the ground state, is a macroscopically large number. So although mu never really reaches 0, it gets very close to 0. So what we have been saying so far is okay. You can actually take mu to be approximately 0 when the ground state starts becoming macroscopically occupied. But the whole solution to the mystery that we were looking at, where did the particles go, is that these particles go into the one state which we did not count when we took our density of states, which is the ground state. And this ground state will have a macroscopically large number of particles now, a large fraction of the particles that exactly the particles that were missing a while ago. Okay, so now your count has to be modified. Your count is no longer mkbt by 2.6, sorry, by 2 pi h cross square you had g 3 by 2 z before. This was the formula. But now the maximum value this could have, you have to replace this by 2.612. But once temperature falls below Tc, this number is too small for n. Where are the rest? The rest are in n wave. The number of particles per unit volume, of course, that are there in the ground state. The reason why we are spending so much time on this is this macroscopic occupancy of a given state, given microscopic state. That is actually going to be important in all the phenomena that we are going to look at. Of course, occupancy per unit volume. Now, remember we had this formula for Tc. This was mkBT by 2 pi h cross square. Right? So you start with the number of particles in your system. This helps you to get Tc. Now, can you just see that this easily changes our expression here? And if we were to rewrite this, this would simply be n into T by Tc. Right? Because this bunch of constants that you have, that's actually exactly equal to this, except that T has replaced Tc. Okay? So we get our formula for the fraction of particles which are there in the ground state, given by 1 minus T by Tc, the part 3 by 2. Or again, it's useful to take a look at what this looks like. When T goes to 0, that is, when you get to absolute 0, this thing is 0. What that means is all the particles, n0 by n is 1. So all the particles, all the bosons go and sit in the ground state. So you have full occupancy of the ground state, all particles there. And this fraction n0 by n keeps on decreasing as temperature rises and reaches 0 at T equal to Tc. So the graph somewhat looks like this. Although my drawing is very bad, but I hope you can make out what I wanted to say here. You get a graph which sort of, oops, it's becoming worse. At Tc, this drops to 0. Of course, it doesn't mean that at Tc or beyond, there are no particles in the ground state. It just means that this ratio, sorry, I plotted this wrong. This is n, I wrote this wrong. This is actually n by n0, of course. That's what I had written. That's wrong. It's n0 by n. The fraction of the total number of atoms which are there in the ground state, this ratio, that drops to 0 at T equal to Tc and stays 0 when T goes beyond Tc. That is, increases beyond that. But you have to realize that we are not saying that there are no particles in the ground state for T bigger than Tc. All we are saying is now you have a microscopic number of particles in the ground state. Maybe 1, maybe 2, maybe 1,000. But that's way, way too tiny compared to the total number of particles, which is of the order 10 to the 20s or 23s or whatever. So this ratio will become so small that for all practical purposes, this becomes 0. Okay. So this is our Bose-Einstein condensation phenomenon, that once temperature drops below this Tc that we calculate using this, our count of particles seems to be too low. And that's because our count of particles missed out the particles which were in the ground state. And so now a large, macroscopically large number of particles go into one quantum state. And that is very important because now you have a macroscopic number of particles which together can show quantum phenomenon. And this, so you have quantum behavior at a macroscopic scale. which is exactly what superconductivity and superfluidity are examples of. Now, as I said before, real superfluids or real superconductors are states with where particles interact among each other, and that becomes very important in deciding what kind of behavior the system will have. So this cannot be a perfect picture of a superfluid or a superconductor simply because here we have assumed that we have particles which do not interact among each other at all. But this is a good enough starting point to show that a phenomenon like this occurs where a macroscopic large number of particles can go into the ground state. A few more important results for this, which we will not these, but their modifications will be needed later as well. Another important thing is energy. How much is the energy that
Sir,
yeah,
sir, if T is greater than Tc, then we can easily write the formula that N equals to m kBT by 2 pi h square whole to the power 3 by
3 by
2
2
into
times
2
G3
point.
by 2 Z.
Yes.
So
Then
instead of
that
2.61 to now you have G3 by 2 Z. So Z, of course, now adjust itself so that N stays the right value. Okay. But note that in this calculation, we had not counted any particle to be in the ground state. Okay.
yes, sir.
And that, of course, is not exactly correct because there will be particles in the ground state. But if you have a finite number of, say, microscopic number of particles, and here microscopic means 1, 2, even hundreds of thousands, it doesn't matter because then n0 by n will be so tiny that we will not be able to see that. That's why it will look like 0. Okay.
Okay, sir.
So it's not as if you don't have particles in the ground state beyond that. It's just that you don't have a macroscopically large number. So that beyond Tc, that is at temperatures above Tc, the system will not show quantum behavior at a macroscopic scale. Okay, so coming to this, the energy per volume will be given by this. You will have G epsilon, D epsilon as the number of states between epsilon and epsilon plus D epsilon per unit volume, divide by or multiply by the Bose-Einstein factor, because I've got the sign wrong here, is -1. And that, of course, would have given you the number of particles between epsilon and epsilon plus D epsilon, but you have to multiply that by the energy to get U by V. Okay. And if you carry out this calculation, okay, the calculation can be done very similarly. It's going to be m to the 3 by 2 by root 2 pi square h cross cube. That's coming from the G epsilon. G epsilon and epsilon to the half. We have an extra epsilon there. So epsilon to the 3 by 2 D epsilon, eta epsilon minus mu minus 1. And quickly going through the same steps as before, this is going to be m to the 3 by 2 by root 2 pi square h cross cube. And using beta epsilon equal to x as before, and so that's beta to the power 5 by 2, which will come from here. 1 by beta to the 5 by 2. And then this formula factor, which is, of course, e to the power x by z minus 1. And this is something which now this is something which you have seen before, last calculation directly. This is it's a 3 by 2. That's exactly 1 by to the x by z minus 1. So what is this integral going to be now? Remember the last one, this should be pretty easy for you to work out. What is this integral? We worked out this integral actually in the last class. We did it for any alpha.
So
So
that's gamma of alpha plus 1
Comma
is
G alpha
yeah,
plus
this
1
is
Z.
gamma 5 by 2, right? And times g 5 by 2 z, which is of course nothing but sum over all p going from 1 to infinity. Okay. And gamma 5 by 2. Let's, anybody remember how much gamma 5 by 2 is?
So 3 by 4 root pi.
Okay, 3 by 2 into root pi by 2.
Into root pi
I'm
by
writing
2.
it simply because this root pi by 2 along with this gave us the similar formula that we had before, right? This mkbt by 2 pi square h, sorry, 2 pi h cross square to the power 3 by 2, the one which we had for n, that came with this root pi by 2. Then you have a 3 by 2 kbt times that and a g5 by 2z. Okay, so our formula u by v is 3 by 2 kbt. Now 3 by 2 kbt should look pretty familiar, right? Then you have this mkbt by 2 pi h cross square to the power 3 by 2 g5 by 2z. Now, is this formula valid when t falls below tc? We had this formula for n, remember, which was simply but this formula was valid only when t is more than tc. When t fell below tc, you have to replace this by, well, you have to either write this as n equal to n0 plus something like this with a 1, or you could simply say this is n kb tc by 2 pi h cross square to the power 3 by 2 times g3 by 2 of 1. Right? This really is not a formula for n any longer. That's a definition for tc, but that definitely holds when t is less than tc. Question is, when this formula for u, what temperature range is this valid for? When I'm asking you this, let me point out that the problem that we had earlier was that we were missing out on the ground state, right? In our calculation, when we wrote our G epsilon, D epsilon, we were not counting the contribution due to the ground state. That's why our calculation for n went wrong. Okay. And when is that an issue? It's an issue when the ground state is macroscopically occupied. If it's microscopically occupied, it's just a few particles. Missing out on a few particles will not really make a difference. But for a macroscopic occupation of ground state, missing up on that will definitely make a difference, right? So when T is less than Tc and you have a macroscopically large number of particles occupying the ground state, not counting the ground state made a big difference. That's why our n came out all wrong and we had to change that. Write that as n equals n0 plus this expression with z equal to 1, right? So can you tell me what will happen to the energy? Will this be valid when T is less than Tc? It is okay when T is more than Tc, no problem. Because when T is more than Tc, the ground state, no state is macroscopically occupied, so we have no issue. When T is less than Tc, what happens? Is this still valid?
So I think it should not be valid.
Why not?
Again, we are missing some particles, no?
Exactly. But how much is the energy of those particles? Not some particles. Missing some particles is not a
No,
problem. You
macroscopic.
will always miss some particles. We are not counting the ground state anyway. But missing a few doesn't make a difference. Missing a macroscopic number does.
Macroscopic. Yes, yes.
But what is the energy of these macroscopic number of particles? The energy in the ground state, how much is that? Yes? Quickly, that should be easy. How much is the energy of a boson in its ground state? What was the formula? Epsilon is given by h cross square k square by twice. What's the lowest possible value of this energy? That's the ground state energy, right? We have been using that fact. What is it? Come on, these are simple things. I'm not asking a difficult question. How much is the lowest value of this?
Three by two kBt.
Lowest value, not the average value. 3 by 2 kBt is the average value. I'm talking of this quantity, epsilon equal to h cross. That's the energy of a particle in a given macroscopic state with the wave number k. What is the lowest possible value which this will have? And in fact, we have used this. When we say things like mu cannot exceed a particular value, we have used the fact that energy cannot go below a particular value. Which is what? Okay, this is such a simple question that I think you are missing the point. You're trying to you are thinking that I'm asking you a difficult thing. Lowest possible value of this. Yes? K has to be K has to have components which are multiples of 2 pi by L, right? What's the smallest possible value for K? You do agree that epsilon will decrease with decreasing K, right? The lowest possible value for K is how much?
So pi by L.
What? So pi by?
L 2
This
pi
was
by
what
L.
the K vector looked like, right? 2 pi
Yes.
by L,
2
nx,
pi
ny,
by L.
nz. And K is the length of this. So what is the smallest possible length? Here nx, ny, and nz are integers. Yes.
0.
0, of course. In fact, we have been using that, right? We have been saying that mu cannot go below above 0. Why? Because the lowest possible energy is 0. And if mu went above 0, then you would have negative occupation numbers. So we have used that throughout. So now can you tell me, because the energy of the particle in the ground state is 0, will this formula still stay valid when T goes below Tc?
Yes, sir. It will stay valid.
Yeah, because the particles that we are missing in this count, we are missing a macroscopically large number of particles this way. But those particles all have energy 0. So the energy doesn't change. We are not missing out on any particles with non-zero energy. When we were counting number of particles, of course, we are missing out a huge number of particles. That's why you need to modify the formula. For energy, you are missing out a huge number of particles, but all these particles have 0 energy. So the energy calculation comes out right. So even when T is less than Tc, this is valid, except that your Z will have to be how much when T is less than Tc? Yes?
Can you repeat the question, sir?
When T is less than Tc, even then this formula will be valid, except that Z will have to take a particular value. How much should Z be?
So 1.
1, exactly. So Once T falls below Tc, Z reaches its maximum value, 1 stays there. So now, if you look at small u, which is the number of particles per, the energy density per particle, that is u by v divided by small n, that is, or capital, or you could write this as capital U by capital N, energy per number of particles. Small n, remember, is capital N by V. So the volumes cancel out, and you end up with this expression. If T is bigger than Tc, take a look. This is what U by V looks like. And this is what N looks like. So if you divide this by this factor cancels out, and you are left with kBt times, well, G5 by 2Z, right? This is for T more than Tc. For T less than Tc, now you have to divide by this. So now it becomes slightly more complicated. It becomes 3 by 2 kb T to the power 5 by 2. Everything else cancels, but you have a T to the 3 by 2 times a T, that's T to the 5 by 2, which is divided by Tc to the power 3 by 2. And then there's D5 by 2, 1, which is zeta 5 by 2, of course, by G3 by 2, 1. Is it clear to everybody? Why you have these two different looking expressions?
Yes, sir.
Yes? Yes. Anybody has a question about this? Please let me know.
Sir, I have a question regarding something
Yeah.
else. Sir,
Yeah, go ahead.
you said that we are leaving out the count of energies from no, you said that we are taking count of the energies from E to E plus DE, but we did
Yeah.
not mention anywhere that what is the value of E or anything specific.
No,
Then how
that
can
was
we
for
say-
that's for G epsilon, right?
Yes, sir.
G epsilon, D epsilon was G epsilon times D epsilon, where the number of states between epsilon and epsilon plus D epsilon. Okay.
Yes, sir.
There we did not say how much epsilon is. Of course, this result will depend on epsilon. G epsilon changes when you change epsilon. But in order to find out the total energy of the system, this is the total energy. What did we do? We took all the possible values which epsilon can take from 0 all the way up to infinity and integrated them.
Mm-hmm.
That's why we have to integrate. For the total number of particles, we have to integrate from 0 to infinity.
Mm-hmm.
The same here.
Mm-hmm.
The only real point is this integral, that is this changing of the sum over all the states into an integral over energies. This calculation loses out entirely on the ground state. Okay? Because G epsilon is 0 for the ground state, we are not counting it at all. And as I said, usually it doesn't make a difference. If the ground state has a few particles, who cares? A few particles have gone missing. But the whole new thing that happens here is a macroscopically large number of particles can go into the ground state, and that's basically because of this result. That sorry, let me go back a bit. When mu tends to 0, the occupancy of the ground state tends to infinity. Or to be more precise, when the occupancy of the ground state is macroscopically large, mu gets to be a very, very small value, minus kBt by Nz. Okay. So you can put a huge number of particles in one state, which is what this condensation is all about. If you have particles with a finite, small number of particles in every microscopic state, you don't get to see quantum mechanical behavior at a macroscopic scale. You get to see it when one microscopic state has a huge number of particles, which is what the Bose-Einstein condensation is all about. And in this calculation, when we talked about the energy, you missed out on those same particles, but they did not make a difference to the energy calculation simply because these particles all had 0 energy. So not counting them did not get your energy wrong. It did get your number of particles wrong, which is why they talk about macroscopic occupation of the ground state. But that did not make a difference for the energy. Okay. And after that, is this okay with everybody? This ratio? Now, one thing, if T is much, much bigger than TC, that is Z is very small, Z now becomes small. So can anybody tell me what this ratio is then? When Z is very small?
So one.
1, because G5 by 2 Z looks like Z. G5 by 2 Z is
Yes.
actually Z plus Z square by 2 to the 5 by 2 and so on. So for very small Z, you can ignore this. G3 by 2 Z is Z plus Z square by 2 to the power P by 2 and so on. Once again, these terms can be ignored when Z is very large. Sorry, Z is very small. So this ratio goes to 1. So U goes to a very familiar result. Right? This is what we get for classical particles. The average energy per particle is 3 by 2 kBT. Classical result from the 3 degrees of freedom, half kBT per degree of freedom. Equipartition theorem. Right? And once again, why does this work? Simply because under these conditions, when temperature is very, very high, the de Broglie wavelength of the particles is so small that we can simply ignore the classical quantum behavior or indistinguishability of the particles. Classical mechanics will work fine because the particle clouds are so tiny that you can easily distinguish each particle from each other simply by noting where they are. The clouds do spread the particles out, but not enough for us to be able to miss out on which particle is which is why the classical result comes back. Okay, when T is much, much bigger than TC. When T is less than TC, on the other hand, things are very different. Even when T is close to TC, it's very different. Now, our final physics part, if we talk about of the heat capacity, which is du dt, what is that like? Du dt for T less than TC is pretty straightforward. Into 5 by 2, so that's 15 by 4. So let me just write the whole thing out properly. It's 15 by 4 T by Tc to the power 3 by 2 5 by 2 1. By the way, is this ratio more than 1 or less than 1? Can anybody tell me that? In other words, that's zeta 5 by 2 by zeta 3 by 2. Is this more than 1 or less than 1? And of course, play with a calculator or write a program which will tell you what this ratio is actually. But any idea how, but you should be able to figure out whether this is bigger or this is bigger. Which one is bigger? This one or
The
this one?
zeta of 5 by 2 is bigger than zeta of 3 by 2. So the ratio should be greater than 1.
Why do you say it's bigger than? It's bigger just because it has a bigger argument. Is that what
Mm,
you're saying?
so am I wrong?
Nah, it should be less
Yeah, you
than
are.
1.
Oh,
No, this is what that is, right? Is that okay?
yes, sir.
So this, of course, has smaller numbers. Larger powers means larger denominators, right? So if you compare the two, once again, the comparison clearly tells you that this is larger. When Z is very, very small, you have this Z, Z square, etc. When Z is very, very small, you ignore the other terms. Both of them go to 1. But otherwise, G5 by, if forget zeta, even in general, G5 by 2 Z is smaller than G3 by 2 Z. Simply because in the series of G5 by 2 Z, you have larger denominators, so smaller values. Okay? In fact, this value is, this ratio is roughly half. It's close to 1/2. Not very important exact value, but you have to realize that it's really smaller than 1. Now, if you're going to try to plot the CV against temperature, what will this look like? This formula tells you at least below TC, this is easy. When it's much, much bigger than TC, how much is it, by the way? What is the derivative of U with respect to temperature when temperature is very, very large, much larger than TC? When T is much larger than TC, you know this is U. So what's the derivative?
So it's a constant 3 by 2 kb.
Yeah, and that's the classical result, right? 3 by 2 kb per particle. That's the classical result for free gases. So when temperature is very, very large, it reaches this 3 by 2 kb line. On the other hand, when temperature is smaller than Tc, we know what the formula is, T by Tc to the 3 by 2. So it keeps on, starts at 0, inclines, and you can easily figure out that at T by Tc, at T equal to Tc, this ratio is 1, and then this becomes 15 by 4 times around a half, right? So slightly smaller than 2 kb, bigger than 3 by 2 kb. So it goes below above that, and then it's not a constant, by the way. It might look like, if you are a bit careless, this formula for T less than Tc, it looks like this is going to be 3 by 2 kb into this quantity. But this quantity also depends on temperature, right? Because as you change your temperature, n number of particles staying fixed means this quantity is going to keep on changing, because Z has to keep on changing to keep n right. And therefore, it's going to be a bit more complicated. But if you calculated the thing out, you would get something like this. And so this shows that at T equal to Tc, you have a phase transition. The heat capacity is no longer a smooth function of the temperature. It actually has a bend here. This is a cusp. That is, the derivative is continuous. There's no jump in the heat capacity, or the heat capacity doesn't become infinitely big. It goes to a finite value, but what you get is a change in the derivative. It was rising up to this point, then it goes decreasing. Okay, and that lack of smoothness in CV shows that you have a phase transition here. So you had a bosonic condensate on one side and normal Bose fluid on the other side, and between them you do have an actual phase transition. That's also going to be very important, because this transition, when you talk of superfluidity or superconductivity, the phase transition aspect is going to be very important. And we will see that because of the interactions present, the phase transitions there will differ in nature from what happens for the free Bose gas. So the free Bose gas does give a model of macroscopic condensation of large number of particles into a single microscopic state, which will be a model for superconductivity and superfluidity. But those effects also have to talk about, there you also have to talk about interparticle interactions and so on. So there are differences. This is not going to be exactly the same for superfluidity or superconductivity. Okay. So next day we are going to start with a study of superfluidity, where we talk about particles which interact with each other. But before I go away, I hope today you have time, right? Today you don't have another class. Right?
No, sir.
No, sir, meaning no time or no class?
No class.
Okay. Anyway, don't worry, I'm not going to keep you forever. I'm just going to let you go soon. But what I want to point out is what we have studied so far is a model of macroscopic condensation, which is a very simple model, non-interacting particles, which still will give us a good view of what happens in superfluidity and superconductivity, but we have to be careful. Because here you have no interaction, certain results follow, which doesn't really work for those systems. But before we completely leave this, one important thing, which is, okay, does bosonic condensation occur in 2D? Two-dimensional systems is very, very important nowadays. So the question would become, and in fact, many of our superfluid, not superfluid so much, But when you have superconducting systems, especially the high temperature superconducting systems, have electrons which are essentially confined to two dimensions because of the kind of crystal structure that we have there. So the question of Bose-Einstein condensation in 2D becomes very important. But now, let me just point out that what will happen in 2D? Okay, first of all, you have to again look at G epsilon, D epsilon. So in 2D, is a volume will have an area, and 2 pi by L will be the discreteness in the lattice. So unlike in 3D where you had a by 2 pi whole cube, v by 2 pi whole cube, here you will have a by 2 pi whole square. Not a big deal. But what about this area between two shells? That was 4 pi k square dk. What will be the case now in 2D?
So 2 pi k dk.
2 pi k dk, exactly. And that actually is a big difference. So, okay, let me not worry too much about the factors. You can put in the factors yourselves. It goes like k dk, right? But remember, epsilon is h cross square k square by twice m. So this thing really goes like d epsilon. What's the big difference? So g epsilon is actually some bunch of constants. No epsilon dependence. It's unlike in 3D where you had epsilon to the half, here you have epsilon to the 0. Okay? No epsilon. G epsilon for a 2D non-relativistic bosonic gas is flat. There is no dependence on the energy. Okay? Contrast with this with the 3D case where you had an epsilon to the half. Now, if you calculate n here, of course, you have to calculate this by and so there are some bunch of constants outside. There's no epsilon to the half here. Okay. Now, okay, I will ask you to finish the calculation. This integral actually is one which you can explicitly solve by simple substitution. You don't have to look at an infinite sum or anything. This is a simple enough integral to do. And that will give you n as a function of z. Okay. So your task would be to figure out what this constant is actually. That's simply by following this calculation through. Just the same way as we did in the 3D. Find this factor, use this factor, and also calculate this integral explicitly. I assure you this is a simple class 12 level integral, not the kind of thing that you had to do before. And find out n as a function of temperature and z. So what I want you to do in the next class, calculate this out and tell me what your conclusions are about Bose-Einstein condensation in a 2D bosonic gas. Okay. Just find out this calculation, find out this n as a function of t and z. Of course, other things stay the same. Mu cannot exceed 0, so z cannot exceed 1, and so on. All these stay the same. But what your task is to figure out what you can say about Bose-Einstein condensation in 2 dimensions, starting from this, working out this calculation. It's a straightforward calculation, and let me assure you that the integral really is very simple. Much, much simpler than the integral that we had to do here. So let me just write down the question for you. What are your conclusions about this phenomenon of Bose-Einstein condensation? Okay. Now, what we are leaving out here is the recent discovery of bosine condensates which are actually realized in the laboratory. That's a fascinating topic, but how exactly they are created and how they are held together in place by some optical potential, how the cooling is done to that degree. All these issues are technical issues which will take us too far away from our theme. So if you're interested, you can of course read up on the net, or there are plenty of nice books now on actual bosines and condensations and their fascinating properties, uh, which is really a hot topic nowadays. But the next day we are going to move over to superfluidity. But I do want an answer to this question before we start the next class. Okay, so that's your homework. And if you have any questions, you can ask me. But otherwise, I'm done. Yes, any questions? Yes, no, no. I am assuming no. Okay. So bye for now. See you again on Tuesday.
Okay, sir.
Thank you,
Okay.
sir.
Thank you, sir.
Thank you.